Hi geometry students, this is lesson 1 from the next unit that we would have eventually gotten to if we were still in school, but it's not too bad to kind of go through on your own. So if you have your workbook, which you should, go find it, pause the video if you don't have it yet, and turn to page 133 in your geometry workbook. That'll be lesson 1. We're talking about different three-dimensional shapes, which might be a bit difficult to kind of talk about when I can't hold up a 3D shape to you, but you could always Google some of these to kind of get more images of what we're looking at. We are looking at the fancy name for a 3D shape. Well, these 3D shapes. A polyhedron is a type of 3D figure whose surfaces are polygons. We've talked about polygons before. So triangles, squares, rectangles, octagons. Each one of those polygons is called the face of the polyhedron. So if you kind of look down underneath some of these, a cube has 6 square faces. So 6 sides, if you picture like a number dice or number die, whatever. So 6 sides, but every side isn't like a line. Like if you draw a square, you're drawing lines. If you're drawing a cube, you have to draw lots of different polygons. So there's different names, like there's tetrahedron, dodecahedron, so on and so forth. If you've ever played Dungeons and Dragons, you're familiar with some of these dice shapes. But either way, we're just going to talk about some of the basic ones. Specifically, if you have a type of polyhedron with 2 congruent and parallel faces, it's called a prism. So congruent means they're identical. So if I draw one triangle and then draw another triangle, and I made them parallel, so I didn't make it so like one triangle is touching the other triangle. That is not what we're talking about. I'm talking about 2 parallel congruent triangles. These are called the bases, even though it's not on the bottom. And then if I connect my corners, so if I connect these ones, these would be kind of like in the back and this. What I've created is a prism, and those other faces, meaning like this rectangular slanted side right here, those ones are called the lateral faces. Lateral being a word for side we've used before. So the congruent faces that are contained in parallel planes, we just wrote down, those are the base of a prism. And the other faces that are not bases are the lateral faces. I'm not entirely sure why you have to write this out twice. My apologies. And not bases, lateral sides. I wrote lateral faces earlier. You can also think of it as sides as long as you're thinking of sides as a flat surface. Because where the 2 faces meet, so where this triangular face runs into this rectangular face, they only touch right here. So they're touching on a line. That one spot where they intersect is the edge. But if you have lots of edges, so for example, there's that edge going diagonally, there's the edge that's the bottom of the triangle, there's the edge that's the side of the rectangle there, they're meeting at a point. That point is called the vertex. So if I actually had one of these shapes and I threw it at you, if I poked you with it, I poked you with the vertex because it's just a line, a point. But if I took it and I scratched you with it, the line where I'm scratching you is the edge. Now, all of these are 3D things, but if you kind of picture taking scissors and very carefully cutting it along all your edges and then unfolding it, you've made a net, a 2-dimensional pattern that could be folded to form a 3-dimensional figure. Now, we're never going to ask you to do a net of like an icosahedron. That's unreasonable. What we would do, though, is something like this, where there are 6 sides. We have 6 squares, and if they are folded up, they would make a cube. How you picture this can vary depending on just how you're imagining it. So we are going to go ahead and say that this C square is going to stay on the bottom of our shape. So C is the bottom. So picture that you're standing on C here in the net, like you're standing right here. To your right is the side, the square with a D on it. You're going to fold it so it's standing straight up, which is what's over here in this image. It's standing straight up, still next to you. So you just put a wall to your right. But you're also going to pick up the wall to your left over here and stand it straight up. So B is standing up next to you as well. However, B is not on its own. A is attached to B. So here's the edge attaching A and B. So when I flip B standing straight in the air, A is also standing up in the air. But then it falls down. When it falls down, it's our roof. So the top is A. So again, you're standing on C, A ends up above you, D is to your right, B is to your left. So looking right in front of you, if you fold up a side, the front face would be the one labeled with E. Behind you, when you stand it up, would be F. So like I said, these are kind of hard to imagine what's going on. You've got plenty of time. You are welcome to try and cut out this cross-shaped net, cut it out of a piece of paper, and then try and fold it along all these edges, and you could make yourself a cube like that. Seriously, you have time. Try it. But then you can also have some weird ones. So question 2 says, how many rectangles make a cylinder? So if you picture a can of soup, if you were to completely disassemble this can of soup, you would definitely have the circular top that you need a can opener to open. You'd have a circular bottom, which you don't usually open, but you could use a can opener to open that. But that's not the whole can of soup. You have the part where the label is. So if you picture taking some scissors and cutting the label and then unfolding it, it would unfold to be a rectangle. But there's only one of them because it just folds all up into the cylinder. So how many rectangles make a cylinder? Just one. So in this polyhedron, we have a type of prism because there are two parallel congruent faces that are called bases. Those are the two pentagons. So we have pentagon A, B, C, D, E, A. That's the one I'm kind of picturing on the top. But we also have a pentagon J, F, G, H, I. That's the pentagon that's on the bottom. So if I want how many faces there are together, we have the two pentagons. But there's also rectangle DCHI. There's rectangle CBGH, and so on and so forth. There's a lot of rectangles going around this shape. Specifically, if I add them all together, there are 5 rectangles. So if I have the 5 rectangles and the 2 pentagons, there are 7 faces. The one that I picture on the bottom, I already kind of said earlier, that would be the pentagon. Ooh, my tracing skills are poor. That would be this pentagon here. So I'm going to name those corners, those vertices. So if I'm just going to start at any one vertex and then go around in a, not a circle, but go around in order. So I'm choosing to go clockwise. I could have gone counterclockwise as well. So J, F, G, H, I. If I want the front face, this again depends on kind of how you're orienting it, how you're imagining it. Picture the front face. If you started walking toward this pentagon, what would you run into first? And the way I'm visualizing it, you'd run into this flat side first. So you would run into the lateral face DCHI. If we ask how many edges there are, remember those are the ones that are the straight lines that are gonna, you picture cutting you. You could actually trace every straight line. So EA is a straight line. There's 1. AB makes 2. I'm currently tracing the pentagon, which should tell you that already gets us 5 edges. But there's not just one pentagon in here. There's the bottom pentagon. So if you add 5 more edges, you would stop and have 15 sorry, not 15. I can add 5 plus 5 is 10. But again, that's not all of them. You can look at my picture right now. I have not traced every side. I didn't trace AF. I didn't trace BG. I need to connect these pentagons with these edges as well. So if I add up all of those, 5 for the top pentagon, 5 for the bottom pentagon, and then the ones that are kind of sticking vertically up, 5 more, there are 15 edges in this. Then it asks for the 5 edges that form the top base. Again, I'm picturing this top pentagon. So 5 edges. There's 1. We name segments with 2 letters. So I'm going to say segment EA. There's this one. Another edge. So segment AB. There are 5 of them. I'm essentially just asking you at this point, name those 5 segments in the pentagon. So BC, remember order doesn't matter, so if I choose to call that segment DC, you would be just as correct to call it segment CD. And then I also have segment ED, 5 edges. How many vertices? Vertices are the ones that if I threw it at you, it'd leave a little puncture wound. Those are the corners. So the top pentagon gets us 5 vertices, 5 corners. But there's the bottom one as well. I could poke you with that one. I could poke you with that one. There are 5 corners that would leave a little puncture wound if I were to throw it. So 5 on top, 5 on bottom, 10 vertices altogether. The 4 vertices that form the back left face, I'm picturing this is on the back side and on the left. So vertices are just the points. So if I'm only, let me get rid of everything else. If I'm only concerned with that shape, I'm naming those 4 points. E is one of the points, one of the vertices. So I'm not naming 2 letters now because I'm only naming a point. I'm not naming the edges. And there we go. So on page 134, even harder to picture and visualize, is something called a cross section. Some of you are going to, find out that cross sections just might not be your jam. You might not be able to picture these very well. It doesn't really help that your notes on page 134 are kind of crappily copied. But cross sections is, if I start with like an actual pyramid. So this shape, picture an actual pyramid in Egypt, but we want to chop it up. So if you somehow were to chop off the top of the pyramid and I pick it up and I show you what shape I've created, which means this slice that I've suddenly exposed that wasn't exposed before is the cross section. In this pyramid, it would be this rectangular shape. So I don't care that there's a pyramid on top and like a part of a pyramid on bottom. We're not talking 3D when we talk cross sections. We're talking about a flat 2D shape. So for example, number 4A, the exact same pyramid, but instead of chopping the top off, I want to slice the side down. One way you can kind of visualize this is to imagine everywhere the slice touches the original shape. So for example, when I start slicing it, my slice touches here. So the side, that triangle of the pyramid, will touch my slice here. But I'll also have to cut down this triangle. I'll end up also cutting down the side of that triangle, and I will exit the pyramid at the bottom here. So that is the 2-dimensional cross section I'm trying to imagine. Now it's turned, so if you rotate that shape that I just kind of traced, you'd have a trapezoid. So same exact pyramid to start. When we sliced it, it became a trapezoid. So it matters what way you chop it. So on B, I want a vertical cross section. So I'm being clear since it's not drawn. If I actually made a sphere out of Play-Doh, and I took a knife and I chopped it. And I chopped it vertically. So I held my knife vertically and I chopped through the Play-Doh. I want to know what shape I would be looking at when I was done. So remember, it's a flat shape. So if I chop it this way and then hold my Play-Doh up, there would suddenly be a circle exposed that wasn't exposed before. Like I said, some of you might be like, what the heck is she talking about? This is hard to visualize without me actually showing you these cross sections. And my screen just froze. Give me a second. No. Let me try again. My apologies. There we go. So a circle. For part C, we've got the exact same square pyramid, rectangular pyramid, depending on how you think of it. And I'm going to make 2 different cuts. So if I cut it horizontally, again, I'm going to start cutting through left to right. So I'm going to hit the shape here. I'm going to cut down these sides, and then I'll exit the shape. So this is the flat 2D part of the shape that wasn't exposed to the air before. So I'm opening it up to show you. In figure 1, we would have what I'm assuming is a type of a square. It might be just a rectangle. But if I chop vertically instead, I'm going to start cutting through the top. And then I'll cut down the left and the right sides, and I'll exit out the bottom. This is very much not a square. It's a rectangle. If I take a triangular pyramid, I'm chopping through it vertically. So I'm starting my chop at the top. I'm going to cut down the shape, so I will have these two downward cuts. And then I will exit. You can't really see where it would exit, but it would exit out the bottom. So if you look at that flat shape that I just traced and ignore everything else, you would have a rectangle. So if I have this pentagonal prism and I'm chopping it horizontally, so I'm going to first start cutting at that corner. I'm going to cut down these sides. I'll have to cut down those sides, and I'll exit out that shape. It's a poorly drawn version of it, but I just traced essentially a pentagon. You'll notice a lot of times the cross section will look like whatever face you're parallel to. So for example, I just made a horizontal cut, and in this shape, the face that's horizontal, I just wrote pentagon. Yeah, it's a pentagon. Whereas in this one, when I chop horizontally, the horizontal face in this shape is a square. So here I'm chopping horizontally. If you look horizontally, this is not a polyhedron, but still. I would start chopping on the outside edge. I would chop all the way through this circular thing. But there's this empty space in the middle here that doesn't have shape. So I would chop here as well. This is one that I wish I had my Play-Doh and I could show you. What you'd end up with is like a flat donut ring or two concentric circles. I don't know how to describe what that name is, so I'm not going to bother trying. So in part G, start with a triangular pyramid. I'm chopping it horizontally, so you can look at what face I'm horizontal with, what face is horizontal in the picture. But I'm going to start by going through this edge. I will be chopping through this part of the triangle and this part of the triangle. And I'm talking about those slanted triangles when I say those triangles. And by making that chop, I'm exposing a triangle that wasn't visible before. I'm parallel with this triangular face. And lastly, on this one, horizontal cross section, when I chop through the front, the sides, those sides, and then the back, I end up tracing the same shape that was on the bottom, just smaller, which is a hexagon. That hexagonal pyramid would have a hexagonal horizontal cross section. So the last one, Eloise has a cube and a right square pyramid made of clay. She's going to put them on a flat surface and then make some chops. And I want to know, how could I get these particular cross sections if possible? So if I start with, a cube. So picture my drawing skills are amazing. Pretend for a moment. I've got these 6 square sides. I should have done this with all of them. Okay, poorly drawn, but there we go. If I cut this and I'm only going vertical and horizontal, if you cut this thing vertically, the vertical faces are squares. If you cut this thing horizontally, the horizontal faces are squares. If you cut a cube, you will only be getting squares. You will never get anything that is not a square, unless you cut diagonally, which we're not doing. If I have a right square pyramid, that means I started with a square. Let me try again. And then actually let me draw it with perspective. So this is a square, but then there's an actual pyramid drawn from it. There we go. So if I chop that thing horizontally, you'll notice the horizontal face is a square. So if you chop the right square pyramid horizontally, you get a square, cross section. But if you chop it vertically, this is where it gets kind of weird and really hard for me to show you, because there's no vertical face on this square prism. Square pyramid is the shape I wanted. Now, when we chopped it earlier, we said we made a trapezoid. Trapezoid's not an option, so I can't choose that one. But what I want to point out is I could actually go through this apex here, the very tippy top point. If I chop it horizontally through that very tippy top point, I will end up having a hard time drawing this for you. I'm going to go right down the middle of the back triangular face. I'm going to go right down the middle of the front triangular face. And then I'll end up chopping right through the middle of the square base. So if you just focus on that triangle that I traced, I get a triangle. So those are the only ones that should be marked. Now, again, if this is like melting your brain, Google cross sections and see if you can find somebody like showing these to you. Or if you have a little sibling with Play-Doh, get some Play-Doh out and start chopping this stuff up, because seriously, when I teach this in class, I usually bring Play-Doh on these days. It's so much easier to visualize if you actually have it in front of you. Do your best. Try the practice. Remember, we're not going to hold it against you if you aren't able to do it. We're just trying to make sure your mind doesn't turn to mush while you're at home, because you still need to be able to think whenever we get back in school. So to hopefully make getting back to school quicker, remember, stay inside as much as possible, wash your hands a ton, and be as healthy as possible.